Good afternoon to all. I'm Rachita from CSC AML Section C. My course topic is essential problems for solving. Topic is magic index. Let's get into the topic. The definition of magic index is an array from A that 0 to n minus 1 is an index I such that AI equals to I. The challenge is that given a sorted array of integers, write a method to find a magic index if one exists. Sorted array. The array is sorted in ascending order. This is a crucial property that allows us to optimize behind a simple linear scan. The distinguished versus non-distinct. Distinct. Values are unique. Easy to optimization. Non-distinct. Values are repeated. Hardest optimization. The native approach. Linear scan. The simplest solution is to iterate through the array from start to finish, checking every element. Fly from 0 to n minus 1 if ai equals to I. Return I minus 1. Time complexity. Linear search is that if the array has 1 million elements, we might check 1 million times. Binary search. For 1 million elements, we only need 20 comparisons. Since the array is shorted, we should not ignore that information. Next. Optimized approach, distinct integers. The comparison. Compare mid index with a mid. The insight. Values increase at least as fast as indices. If a mid less than mid, the magic cannot be on the left. The action. Discard half the array at every step. Similarly to standard binary search. Binary search logic. Decision tree. If A mid equals to mid, then found it return mid. If a mid less than mid, then value is too small, must be on the right side. If A mid greater than mid, value is too big, must be on the left side. Then get into it. The duplicate problem. Why logic breaks? If elements are not distinct, they grow at least as fast as indices. Rule fails. If we type it, the rules fails. Example, A mid less than mid doesn't guarantee the left side is empty. Why? A duplicate value on the left could theoretically equal its index. Solution for duplicates. We must search both sides, but we can prune the ranges. Search left. Search indices from start to min, mid 1, A mid. Search right. Search indices from max, mid plus 1, A mid to end. If a of 0 is equals to minus 1, it is not magic. If a of 1 equals to 0, it is also a not magic. But a of 2 equals to 2 is magic index found. A of 3 equals to 4 is not magic. A of 4 equals to 10 is also a not magic. Magic index equals to 2. Naive approach, linear search. Check every index algorithm that is for I from 0 to n minus 1. If ai equals to I, return minus 1. Time complexity equals to 0 of n. Efficient approach, binary search for sorted distinct arrays. Since the array is sorted and values are distinct, we, we can use binary search algorithm. Divide and conquer. Find middle index mid. If a of mid equals to mid, return mid. If a of mid greater than mid, search left half. If a of mid less than mid, search right half. Time complexity 0 of log n. Applications of magic index. Although academic, similar principles help with solving AI search problems. Optimizing shorted data searches. Optimizing shorted. Identifying fixed points in mathematical functions. Debugging array or index mapping algorithms. Concept. Magic index. Index I where AI equals to I. Best case. Binary search if array sorted and distinct. Time complexity O of log n. Practical use efficient search AI algorithms. Python code is used for this magic index. Find middle index mid. Since the array is sorted and values are distinct, we can use binary search. This means the value sorted at that index is equal to the index itself. AI equals to a magic index is an array is an index I for I from 0 to n minus 1. If a of I equals to 1, return minus 1. Time complexity is 0 of n. Efficient approach of binary search. Although academic, similar principles help with solving AI search problems, optimizing shorted data searches, identifying fixed points in mathematical functions, debugging array or index mapping algorithms. Concepts. Concepts are magic index, best case, time complexity, practical use. Those are of magic index for index I where AI equals to I. Best case, binary search if array sorted and distinct. Time complexity, O of log n. Time complexity, O of log n. Its practical use for efficient search AI algorithms. Solving AI problems. And that if a mid equals to mid, it is called return mid. If a mid greater than mid, then the search for left button. If a mid is less than mid, search right half. Then key takeaways. Brute force is safe. O often works for all cases, but it's slow for large data sets. Distinct values allow log of n. We can discard half the search space confidently. Duplicates require hybrid search. We prune ranges based on values, but worst case complexity degrees of O of n. Magic index is that index I, where A of I equals to I. Time complexity is that O of log n. Practical use efficient search AI algorithms. That a magic index is an array is an index I such that A of I equals to this means that value sorted at that index is equal to the index itself. The example given a sorted array of distinct integers a equals to -1, 0, 2, 4, 10. Among these, the magical index is 2 because a of 0 equals to -1, it is not a magic. A of 1 equals to 0, it is not magic index. A of 2 equals to 2, it is a magic index found. A of 3 equals to 4, it is not magic index. A of 4 equals to 10, it is not magic. Naive approach. It is meant by linear search. Check every index. That algorithm is for I from 0 to n minus 1. If a of I equals to I, return minus 1. Time complexity 0 of n. Efficient approach. Binary for sorted distinct arrays. Algorithm divide and conquer. Find middle index mid. Time complexity o of 0 of log n. That the applications of magic index, although academic, similar principles help with solving AI search problems, optimizing sorted data searches, identifying fixed points in mathematical functions, debugging array or index mapping algorithms. Brute force is safe, works for all cases, but is slow for large datasets. Distinct values allow. We can discard half the search space concurrently. Duplicates required hybrid search. We prune ranges based on values, but worst case complexity degrades on O of n. Thank you.